Let's look at the Thevenin and Norton equivalent circuit, and in this case, we're gonna look at through this example. We're not gonna do the full explanation of the theorem itself. So here, the example we had here is to find the Norton and Thevenin equivalent circuit for the sub-circuit in the dotted box, or this can be equivalent wording as the equivalent circuit seen by this capacitor, right? So in that case, we need to isolate the circuit from the rest of the circuit. So we can do the open circuit voltage, and in this case, we can isolate this circuit here. So this is and we do the open circuit voltage. So we call the VOCS, and here that means the current is 0, right? So I have IS here, I have LS here. So in this case, the open circuit voltage is going to be equal to Thevenin equivalent voltage. That's going to be equal VOCS. The VOCS in this case, since this voltage here is current is 0, so the voltage here this is 0. So therefore, the VOC just equal the voltage across this inductance impedance, right? So therefore, the voltage across this here is just equal, this current is equal IS because this current here is 0, right? So therefore, this is going to be equal IS times LS. So this is the open circuit voltage, and we can also find the Norton equivalent circuit current by finding the short circuit current. So we still isolate this current in the dotted box here. And now in this case, we draw the circuit and we short the terminals here. And we're trying to find IS sub SCS, which is the subscript SC stands for the short circuit, as the subscript OC stands for the open circuit. So we still have I sub S here, and in this case I have LS, I have R here. In this case, this I sub SCS is just a current through this resistance, and we can use the current division, right? So in this case, I sub SCS is equal to the current division. You can use two different ways, right? You can use, let's say you use the admittance, that's fine. If you use admittance, in that case, that's going to be 1 over R over the sum of the admittances, right? Times the IS. Or you can use the impedance. So in this case, that's going to be LS divided by R plus LS. So that in that case, you need to use the other impedance. Okay, the other impedance. Actually, from the first one here, if you multiply this by R times LS, right? And you get the second one, right? You multiply the numerator and denominator by the same R times LS, and in this case, on the numerator you're left with the LS, on the denominator you're left with R plus LS, right? So this is the Norton equivalent circuit. So this I sub N S, and now the impedance. The Z sub N is always equal Z sub T, and Z sub TS, that's equal VOC S over I sub ISCS, right? So VOC is equal to, we just get that, so that's equal LS times IS, and for the Z sub N, right? For the I sub SC, that's LS divided by R plus LS times I sub S. So I sub S, IS is cancelled. So in this case, we're gonna equal LS times the inverse of the denominator, which is R plus LS divided by LS. So I hope this math really in detail now. That's equal R plus LS. Okay, so we can find the three parameters, and in this case, the Thevenin equivalent circuit would be Z sub TS, right? Z sub t s, which is equal, no, V sub t s, the voltage source, and here this is Z sub t s, and that's seen by that capacitance 1 over Cs, and the Norton equivalent circuit would be Z sub n s here, and I sub n s, and in this case, this capacitor impedance still sees this circuit. And now this is known, right? So we already find this. This is how we find the Norton equivalent circuit. And we also know that there's looking back method. You can find the impedance, the Thevenin or Norton equivalent impedance by looking back. The looking back method is by using the looking back method for if we use the looking back method, we can just turn off the, so in that case we turn off the source, right? To turn off the source, we draw the circuit. In this case we have let's see, the original circuit we have here. So we turn off this so in this case we turn off this current source. We have the resistance here, we have the inductance here, so you have the open circuit here. So looking back, so this is the ZEQS, and the equivalent circuit in this case, equivalent impedance ZEQS is just equal R plus LS. Very simple, right? So this ZEQS is going to be equal ZT and also equal ZNS. Right? So this is the how we find the Thevenin and Norton equivalent impedance using the looking back method. And in this case, I think this will conclude all the three sections of this lecture. And I hope you enjoyed the math derivation, especially in the second clip. And I'll see you next time. Remember, no matter what you do, just keep going. You can't stop, right? Just keep going. See you next time.